So non-ferrous alloys is the topic which we're going to discuss today. So what is the difference between non-ferrous and ferrous alloys? Ferrous alloys contain iron, non-ferrous alloy doesn't contain iron. And when it comes to the topic non-ferrous alloys, what we're going to discuss in the coming slides is about magnesium. The first one is non-ferrous alloys and its alloys, and the second one is titanium and its alloys, third one is aluminum and its alloys. So these are the three types of non-ferrous alloys which are used in automotive applications. So what are the main objectives of this non-ferrous alloys? So non-ferrous alloys, as I told you, it doesn't contain iron percentage, and they have a good percentage of other metals, and they're extracted at different sources. So we extract this one from the earth core in different forms, and then we try to we have a process where we try to remelt it and make it fabricated. So I'll be explaining in the upcoming slides. So first non-ferrous alloy which we're going to discuss today is about aluminum alloy. So first is about magnesium alloy. So what is magnesium? So magnesium alloy, and the objectives of what are the subjects of interest is we're going to discuss about the introduction of this magnesium alloys, and then the production of this magnesium alloys with different types of magnesium alloys, and the extraction of what is the types of extraction you do for this magnesium alloys, along with the melting and casting process of this alloys. So what is the process you're going to do once you're extracting it? When it comes to the objectives of this topic, what you're going to discuss about the alloys of magnesium is the topic provides a fundamental knowledge of different methods of production, like heat treatments of this magnesium alloys, and use of various types of cast and wrought magnesium alloys, and also the influence of this magnesium alloys on different microstructures of different materials, and also the heat treatments are mentioned according to this, and we discussed with the relationship between the appearance of this different types of magnesium alloys. So these are objectives what we're going to discuss about magnesium. And when it comes to introduction, magnesium alloy is generally found 2.8% in seawater in the forms of, the first one it's going to get in the form of dolomite. This one is dolomite, which is the main extracted material of magnesium alloy, and the second one is it's magnesite. The second one is magnesite. So this is magnesite, and the third one is cementite. So the third one, whatever we're going to discuss, is about cementite. This is the third type of material. So these are the three types of materials how we generally magnesium is extracted from the seawater, and they have different chemical formulas as explained. So the dolomite has a chemical formula of, as explained, we have Ca, calcium magnesium oxide with carbon dioxide. So this is about magnesite. And when it comes to magnesite, it is magnesite, so it's magnesium carbon dioxide, CO3. So these are the two different types of magnesium alloys what are generally seen in seawater. They are 2% of they're extracted from 2.8% from the seawater, and the rest is available from the earth crust. And it's generally found in United States, England, Australia, and Germany, and also in Thailand. Normally it's available in Thailand in the form of dolomite and magnesite. So, and magnesium has maximum percentage of purity, which is about 99.8%, and it's generally available for various. We use this one for various types of engineering applications. So the diagrams below is shown. It shows you, the first one shows you the dolomite structure, and the second one shows you about the magnesite structure, and the third one shows you the structure of cementite structure. So these are the three types of structures what we have for the magnesium, and this is a general view of magnesium alloy. So where do you get this magnesium alloy? How does it get extracted, and what are the different forms and by forms you're going to get from magnesium alloy? And then when it comes to the applications of this magnesium alloy alloys are used in various applications, such as they are used in cell phones. They are used in cell phones. They are used in laptop frames. You know, the laptop frames, whatever we have, they are used in laptop frames. They are used in automotive applications, where we are going to use it in the alloy casing, and also going to use this one in gearbox casing in Volkswagen. The present Volkswagen engine, you're going to use this one. Since it's made not much tougher than iron and steel, we try to use this magnesium. So, and also it is used in aerospace applications. So this is the general applications, whatever where we try to implement this magnesium alloy. And when it comes to the introduction of this, as I explained you, so when it comes to the physical properties of magnesium, magnesium has got has a crystal structure of HCP, as you studied before, and it has an atomic diameter of 0.320, and it has a density of 1.73 with a melting point of 650 degrees centigrade. And when it comes to the alloying elements of this magnesium, the magnesium is alloyed with different materials such as aluminum, zinc, argon, and silicon. And when it is combined with different materials, so what happens here is when it's alloyed with aluminum, zinc, magnesium, and other rare metals, it produces alloy, and it's going to reduce its strength. Normally, its strength is quite less, but when it's alloyed with other materials, the strength increases, and also it has influence of reducing the weight. And it tends to form compounds with negative valence ions. So due to strong electropositive rather than solid solution. So rather than having a solid solution, they have a tendency to produce a maximum negative valency. So they have positive and they have negative valency. So they produce negative valency. What it does, it improves the solid solution structure of this magnesium, and it's not readily plastically deformed into different types of materials. And what would be the drawbacks of this magnesium is the last one. So it has normally so what you can see here, it has normally low strength, and it has toughness quite less when compared to other materials, and also it is corrosion resistance. So the applications are quite limit for this magnesium alloy when compared to other types of alloys. And also it is easily flammable with oxygen. So in the presence of oxygen, it gets fired easily, or it can get disturbed quite easily. So these are the physical properties of magnesium. So when it comes to the production of this magnesium alloy is generally extracted in different processes. So you're going to extract it, as I told you, it's in different forms such as dolomite, cementite, so it's in different forms. So how do you extract it? So we have different extraction processes from the earth crust or from the seawater. So the different types of extraction process I have explained here. You can see we have calcination, we have Pigeon process and Dow process. So these are three types of extraction process which I will be discussing in the next slides. So we have calcination, we have Pigeon, and we have Dow process. And what about the fabrication? Once you get extracted, then you need to do fabrication. So the fabrication process of this magnesium alloy, the first one is that you do casting, and then you have casting is done by two means. It's going to change for depending upon the alloy. So the casting process of this magnesium alloy is sand casting, and another one is die casting. So these are the two types of casting techniques what we generally use for this magnesium alloy. And when it comes to the forming process, we have rolling, forging, and extrusion. So these are the general for forging process for this magnesium alloy. And then when it comes to the extraction of this, so calcination is a process where you're heating MgCT, magnesium carbonate, MgCO3, to produce magnesium oxide, MgO, which is going to mix with petroleum and coke, and then it is getting separated from heat, separated with the presence of heat to get magnesium and oxygen, one molecule of oxygen left over. So what are the different metals, whatever you get are depending upon the structure of the given material. So what happens here is completely defined, and this is the first process what we're going to discuss is about calcination, where we have MgCO3 is generally you're going to get from MgCO3, this is getting reacted this one. So you're getting what? So you're getting from this, you're getting MgO, and then when this is mixed with coke, when you're going to mix this along with coke and at a given temperature. See, the first process what you're going to do in calcination process, you have magnesium carbonate, which is gone through this calcination process. From this you get magnesium oxide, and magnesium oxide, the second process, when it is mixed with coke, you're going to get it is going to get separated as magnesium and oxygen. So you get two metals. From this you get magnesium. So this is about calcination process. In between this you have calcination process occurring. So this is the general process. I'll be explaining in the next slides. So this is about calcination process. And then when it comes to thermal reduction method, or you call it as, we have another method which is called as Pigeon process. Pigeon process is completely new, and it's completely newly invented by the current researchers. In this process what happens is, the powdered ferrous silicon and magnesium oxide is discharged, or it is charged in a furnace. So you have this one ferrous silicon, and we have magnesium oxide, which are charged heated in a vacuum at a temperature of 1200 degrees centigrade, and then you have magnesium vapor, which is condensed in the form of crystals. Once again, I'm going to explain you the periodic process is quite similar as the first process, calcination process. But in the thermal reduction process, what happens is ferrosilicate with the magnesium oxide. So we have powdered process, as I told you, periodic process is thermal reduction process where we have ferrosilicate and magnesium oxide which are completely discharged in a furnace at a temperature of 1200 degrees centigrade, and this gives a magnesium vapor, and the vapor is condensed in the form of crystals. So this is the second type of process. And when it comes to third type of process, which is called as Dow process, the third one, as you can see, so it's also called as electrolysis process, where you try to apply a current. So precipitate dolomite, whatever you get the dolomite from the extract from the earth core, which is in the form of precipitate, and seawater, is treated with HCl, hydrochloride, to give MgCl2. So what happens is the dolomite, what you're going to get, the dolomite which is extracted from the earth core, from the earth, okay, earth crust, which is extracted from the earth crust, is taken out, and this is actually what you do is you try to charge it. So you try to heat it with, or you're going to mix it with HCl. So when you try to heat it with HCl, you're going to get magnesium chloride. So this magnesium chloride, once you get it, and this is a try to give an electrolysis process applied to this. For this, you have electrolysis applied, electrolysis process, and this what happens is you get, once you apply the electrolysis process, then we have magnesium left over with other element, which is and we have chlorine left over. So you get magnesium like this. So this is the thing what generally occurs. So the same process as I explained you, the two process what I've explained you about calcination and pyrogen process, this process also is quite same. But what happens here is the dolomite what you're going to get from the earth crust is actually mixed along with the HCl, hydrochloride. So once dolomite is mixed with hydrochloride in a you get MgCl2, magnesium chloride. So magnesium chloride, it's undergone electrolysis process. So once the electrolysis process is done for this magnesium chloride, you get magnesium and chloride, which are separated with each other. In this electrolysis process, what happens is, since charge is provided, the chloride molecules get separated from the magnesium molecules. So you get magnesium and chloride. So two different molecules are observed. So this is about the extraction of magnesium. So the extraction of magnesium is completely different to that. So the first one, as I told you, we have three different processes. So when it comes to the calcination process, as I told you before, we have three processes: calcination, Dow process, and we have thermal reduction or pyrogen process. So these are the three types of process of extraction of this magnesium. So when it comes to calcination, you can see, as you can see, we have MgCO3. MgCO3 is calcinated with magnesium carbonate, is calcinated with calcination is done, and you get magnesium oxide. This magnesium oxide, again, it's converted into Brinell form, and it's heated at a temperature of 2500 degrees centigrade. So once it's heated at a temperature of 2500 degrees centigrade, what happens is MgO, magnesium oxide, gets converted into gas. You have gas and solid both. So you have gas. So you're going to heat it. The magnesium oxide, you're going to heat it in the Brinell or the vacuum. So what does it do? It tries to form a vapor. So once the vapor is formed, you get in form of gas, and this is cooled, fast cool. You're doing the fast cooling process at a temperature of minus 120 degrees centigrade. So what happens here is, once you're doing it at minus 120 degrees centigrade, you're getting magnesium in the form of solid. So, and when it comes to the boiling point of magnesium is 1090 degrees centigrade. Above this boiling point, you can't get magnesium. And then the down reaction, as it is written as MgO, Mg when it's reacted with coke. So what do you get? You get both. You get molecules of magnesium and CO. So this is the thing what happens in calcination process. So that's why I mentioned the equation down. So you can see, so when magnesium is reacted with coke, you're getting magnesium and CO left over. So this is the general process, whatever is happening in the calcination process. And when it comes to the second process, what we're going to discuss here is about pyrogen process. It's quite same as other process, but what happens here is you have dolomite, what you're getting from the extract from the earth core is done calcination, the previous process, at a temperature of 1000 to 1100 degrees centigrade. So you're doing calcination, and once this calcination is done, you're going to get MgO plus calcium oxide. So we're getting MgO plus CaO, which are getting after this calcination process, and these are heated same in a thermal furnace. So you try to heat it at a temperature of more than 1200 degrees centigrade in a Brinell. So when you try to heat it in a Brinell, then you get the same form, magnesium gas, and then you condense it, you get magnesium solid. The process is quite same, but the process of making extraction is quite different. As you can see in the previous slide, you get directly you're going to get magnesium carbonate, which is then calcinated, and you're getting magnesium oxide. But when it comes to pyrogynic process or thermal reduction process, we have dolomite, which is done calcination. So the extract, what are you going to get it? It's done calcination process, and you're going to get MgO and CaO. So this is when this is mixed with ferrosilicon and it's pressed, you're going to get in the Brinell. So you're going to get Brinell, and this Brinell, you're trying to heat it up at a given temperature, and you're getting both the same magnesium gas, and then you're doing condensing and you're getting magnesium solid. And there you're doing cooling, here you're doing condensing. So in calcination process, you're doing cooling, but when it comes to a pyrogynic process or thermal reduction process, you're doing condensation and getting magnesium solid. So the magnesium vapor, what you're going to get is then condensed to form crystals, as explained. So this is the second type of process. And when it comes to the third type of process, this is called as electrolysis of magnesium, where we have a process where we have a different thing happening here. So what happens here is you're trying to giving electrolysis process, you're applying electrolytic process to the given material. So what happens, as I told you in the previous slide, we have a different process occurring. So what happens here is, as we know, as I explained before, in the calcination process, the precipitate of the dolomite, what you're going to get is generally available, which is available from the seawater, is taken out and is treated with HCl, hydrochloride, to give MgCl2, magnesium chloride, and then this is put into an electrolyte cell. So what happens is, when this magnesium chloride is put into the electrolyte cell, you're going to get magnesium chloride and magnesium, and you're getting a cathode. So what happens here, this is the same thing. So the electrolytic cell is supplied with the magnesium chloride. So this is about the electrolysis process of magnesium, and it's the same, which you call it as Dow process or electrolysis process of magnesium. So these are the three types of phases, whatever happens in the extraction process of magnesium. And then when it comes to the second one, so this is about magnesium. I've told you the process of extraction of this magnesium and the process of formation of this magnesium, what are the different types of casting process of this magnesium. So when it comes to the third one, which is the titanium, so second one, which is titanium. So magnesium is done, so we'll go to the second one, what is titanium and its alloys. So what are you going to discuss? You're going to discuss the introduction objectives, the extraction of this and melting of this titanium alloys, and then what are the different types of alloying elements and the classification of these alloys, and what is the commercial pure titanium, how does it look like, and we're going to discuss about different types of titanium alloys, such as alpha titanium alloy, beta titanium alloy, and alpha plus beta titanium alloy. So these are the different types, and what are the different types of welding properties of titanium alloys, and what are the properties of titanium. So these are the subjects of interest, what I'm going to teach you in the upcoming slides. So when it comes to titanium, what is titanium? So titanium is generally a metal. So it's generally named after a titan because it's quite strong, and it's a powerful metal when compared to other non-ferrous alloys. Titanium is the strongest one when compared to others, and titanium is the fourth abundant metal on the Earth's crust, which is about 0.86% after aluminum. So aluminum is also rarely available. That's one type of alloy, non-ferrous alloy. But after aluminum, the next fourth abundant metal is titanium, and titanium is generally having only 0.86% in the Earth's crust. So about 0.86% in the Earth's crust is available in the form of titanium only. So and when it comes to titanium is not found in free, pure and metal form. So but in nature, but it is used in the form of oxides. So you get it in two forms, either you get it as limonite and you get it as rutile. So these are the two different forms. How do you get aluminum? So where we have the diagrams shown here. So the chemical formula of these two metals are so for limonite it's TiO3, O2. So these are the two types of metals from where we get titanium, and the extraction of titanium is done from them, as you can see from the below diagram. And then they are found in small amounts in Thailand and also in other places of the globe. So and they have the similar properties when compared to other types of alloys, and the weight of titanium alloys is nearly half of that of steel. So the strength is good, but the weight is half of that. So even the weight is quite less when compared to other metals. So this is about titanium. And when it comes to the physical properties of aluminum, so we have the crystal structure of HCP, So, and then we have HCP and BCC. So it has both structures. Titanium has both structures of HCP, which is formed less than 882.5 degrees centigrade, and we have BCC, body centered cube structure, which is about 882.5 degrees centigrade formed. And the atomic diameter of this titanium is 0.320, and the density of titanium is 4.54, and the melting point of titanium is 1667 degrees centigrade. So what are the general properties, physical properties of titanium? Titanium generally express different ultra transformations. Either it can be in alpha state or it can be in beta state, and it can highly react with oxygen, nitrogen, and other inert gases, and it is difficult to extract. It is difficult to extract, and it's quite expensive when compared to other type of metals. So it is mainly used as watt forms in the form of different types of applications, and we try to use titanium in different applications where we rarely have use. So since it's available and the cost is not critical, and it has got a high strength and it has got a toughness. So this is about the physical properties of titanium. So when it comes So when it comes to the advantages of titanium, as you can see, we got different advantages of titanium. Titanium is generally good it has a low density, it has high strength, and it has got low ductility, and also it has more corrosion resistance. So it has got more corrosion resistance, and it has all these 5 properties whatever I've shown. So titanium is one of the better material when compared to other type of materials. And when you see the graph there, you can see with the different types of metals and with comparison of strength. So you can see titanium is in between steel, iron, and it's between magnesium. So it's one of the good metal, but it's abundantly available. So as you can see from the graph given below, the applications we're going to use this titanium alloy and where it is generally applied. So this is about the advantages of titanium alloy. And when it comes to the applications of this titanium, and when it comes to applications of this titanium alloys are used in various forms. We try to use that one in knee replacement. We try to use it in aerospace applications. We try to use that in automotive applications, and mainly it is used for various sectors. It's abundantly available. So we try to use it in all the sections of this thing. So where we use it in shape memory alloys. We use in turbine blades. We use it that one in automotive applications such as motorcycles. We use that one in also titanium extraction on building different types of materials and buildings. Also we try to use this titanium alloy. So when it comes to the applications, it's classified. You can see, as you can see, it is classified. So aerospace applications, where we try to use it in civil, military, and space applications in aerospace, and we try to use it in medical applications in medical, such as orthopedic implants. So if you want to have any implants into the body, and we use it in bone screws, and we use it in dental fixtures, in the teeth fixtures, and we also use in the fabrication of surgical instruments. When it comes to industrial applications, titanium is used in petrochemical, offshore, subsea, and we use it in general engineering purposes. And when it comes to the specialist applications, where we use it in body jewelry. So titanium is generally used in body jewelries. It is in ultrasonic welding. It is used in motor racing, and also it is used in marines, bicycles, and also other sports equipments. So these are the different types of applications of titanium. And then when it comes to the the extraction process of and production of this titanium alloy, or the extraction process of this titanium alloy. The extraction process of this titanium alloy, since the extraction process I've explained of magnesium, it's quite higher. But when it comes to the extraction process of titanium, there's only one extraction process, that is Kroll extraction process. And then we have melting process. We have different melting process, because that metal, what we discussed, magnesium, no, it have melting process done, but we are doing it in turbine. But this one has got different melting process. Titanium has got, since it's quite stronger than magnesium, it needs to get melted. So the extraction process, you're going to do it by Kroll, and then you're doing melting processes such as electroslag refining. We have the first one, which is ESR, and the second one is vacuum arc melting, which is the second one. Third one is electro beam welding. Fourth one is plasma arc melting, and fifth one is induction skull melting. So these are the 5 types of melting process for this aluminum once you extract it through Kroll extraction process. So when it comes to the casting process, it's quite different. So casting process, we have, as we discussed in magnesium alloy, the casting process either by sand casting and die casting. But when it comes to titanium alloy, since it's expensive, we have two casting process. One is investment casting and second one is laser fabrication. So these are the two types of casting process. And then when it comes the next stage of forming process, it's quite similar as other process where we do the forming process but such as rolling, forging and extrusion. And the final process what you're going to do here is heat treatment. So this is about the production of this titanium alloy. And when it comes to the extraction of this titanium alloy, the extraction of titanium alloy is generally you get it in form of rutile, as explained, rutile and the other one lumetite. So you can rutile is TiO2. So once you extract this one in the form of rutile, when it comes to extraction properties of this extraction of this titanium alloy, titanium ore, what you're going to get from the earth core, as I told you, rutile, and the other one is luminite. So rutile, when you're getting rutile, this is converted into titanium sponge. As you can see in the diagram below, there is titanium sponge, which I have explained there. So we have a titanium sponge like structure. Once you get to that form, this is the byproduct. So you're going to get in different shapes. So this is about rutile, and this is passed through Cl2 gas. So once you get this sponge, this is passed through Cl2 gas and through a charge, through charging the ore. And then once this is passed through Cl2 gas, this results in the formation of a colorless titanium tetrachloride. So we have this TiO2, when it is passed through the Cl2 gas, what you're going to get is, so when this occurs, what you're going to, two molecules of you're going to get. So when rutile, which is extracted from the earth core, is reacted with Cl2 gas. So what happens here is, in the presence of coke, what happens here is you're going to get titanium tetrachloride, TiCl2. We're going to get this, and you're going to get carbon dioxide, which is left over. So this is the process of general extraction of titanium, where we have titanium, the rutile. This is rutile. What you're getting in this one is rutile, which is extracted from the earth core. This is reacted with Cl2 chlorine, so Cl2 gas, and with the presence of coke. So what happens is you're getting titanium tetrachloride, and you're going to get carbon dioxide, which is left over. So once you get titanium chloride, this is the first process. So in the second process, once you get this titanium chloride, this is purified by fractional distillation. So TiC3Cl2, titanium tetrachloride, is purified. This is purified by distill process. So you're doing distillation. Distillation is purification. So you can tell it as a purification process. So once you do distillation, then what happens is the liquid form of this titanium chloride in the third phase, the liquid form of this titanium chloride, since after this distillation it becomes liquid. So what happens is it's reacted with either with magnesium or sodium under the inert gas. So this gets reacted with. So this one gets reacted with either magnesium or sodium. So when this titanium tetrachloride, what you get it from the second process after distillation is available in liquid form, and this is reacted with magnesium or sodium. So once this is reacted with magnesium or sodium under the influence of inert gas, so what happens is you're going to get titanium sponge. The titanium sponge, which as you can see in the diagram there. So this is the titanium sponge, as you can see here. So this is titanium sponge, which is this one is the titanium sponge. So this one what you're going to get. So after getting titanium sponge, this is recycled. So once you recycle it, the magnesium and sodium is removed, and you're going to get titanium in the ore form or in a ingot form. So this is the process. The down process explains you about the systematic process what I've explained through the reaction. So this is about the extraction of titanium, and this is also called as crawl process. As I told you, there's only one process for extraction of this titanium, and this process is called as crawl process. Melting process of this titanium. As I told you, we have 5 melting processes. In the first one is its main important one, which I'll be discussing now, because that is the thing which is more important when compared to other melting process. So the main melting process of this titanium is vacuum arc melting, which is called VAR, or we call as vacuum arc melting. What happens here is we have, as you can see, we have two structures. The sponge, back side. Full antenna. Okay. So we have what happens here is the extraction process of this according to this vacuum arc melting, we have ingots. As you can see, we have ingots. These ingots react with other alloying elements which are present here. You can see the alloying elements. So these alloying elements and these ingots, they mix together, and when they mix together and the welding process is done for them. So when the alloying elements mix with this titanium sponge, whatever is available here, so the titanium sponge and these alloying elements can be in different forms. They can be aluminum, they can be argon, they can be silicon. So these are mixed with the titanium sponge to increase the properties. These are sent to a welding process, as you can see here. So the welding is done, heating is done, and so once this welding process is done, you get it in different shapes. And then what happens here is the main melting process is vacuum arc melting, which we're going to discuss now. So this is quite different to other melting process, but majority of the automotive industries and other industries, they try to use this because this is quite easy, and also it is quite flexible to our standards. So here what happens is, as you can see, we have a sponge. So in this vacuum arc welding, which we try to use it in automotive and other industries because they are set according to the standards of this industrial standards. So what happens here is we have a titanium sponge. So this titanium sponge is which is available from the earth core, is mixed with other alloying elements, as you can see in the diagram here. So these alloying elements can be different from, they can be aluminum, they can be silicon, iron, etc. So these are mixed and they are hydraulically pressed together in the hydraulic machine. So you are hydraulically pressing both the titanium sponge and these alloying elements in a hydraulic machine at a given temperature. So once you try to press them, you get it in the form of briquettes. We call it as briquettes. They are different shapes. So these briquettes are placed into the welding box. So these briquettes are in the form of ingots, small ingots, and these are placed in the welding blocks, and this welding blocks is then heated at a given temperature. So first phase of heating is being done. So once the heating is done, the properties are going to be increased, and then we have the second phase of heating. As you can see, the difference between the ingot size and shape. So in the first process of heating, the ingot is quite lengthier and doesn't have that much diameter, but when you do the second phase of heating, the ingot, what you're going to get, the titanium ingot, what you're going to get is generally big in shape. So the electrode or the double triple is melted because of in the wear furnace to produce a sound ingot. So if you want to get a good ingot, you need to do 1 or 2 different stages of melting process. So this is about vacuum arc melting. This is generally used for titanium alloys for in automotive and other industrial applications, which is generally used. The other 4 are not according to the work, but I'll be explaining you in the upcoming slides. So this is about titanium alloy, and then third one, aluminum alloy. So why we need aluminum alloys? So this is the third type of ferrous alloy. So why do we need aluminum alloy, and what about the production of aluminum alloy, and what are the physical properties of this aluminum alloys, and what are the heat treatments of this aluminum alloy? So when it comes to the aluminum alloy, it's one of the best non-ferrous alloy which is generally used nowadays. We can see it in everywhere. Rather than seeing magnesium and titanium, aluminum is found in everywhere in our day-to-day use. So we'll just learn what is aluminum. So it generally provides a different method. So what does this study of this aluminum provides us? So this provides us complete information of the methods of production of and heat treatments of this aluminum, and also the influence of alloy composition and microstructure of aluminum on different mechanical properties, and also the chemical properties of this aluminum alloys, what we're going to get. So when it comes to introduction, so why we need aluminum alloys? So what are aluminum alloys, and why do we need aluminum alloys? So aluminum, as I told you, titanium alloys are 4th abundant. Aluminum is the 3rd abundant metal, which is found in the Earth's crust, which is only element which has only 8% on the Earth's crust and normally found in oxide forms. So we generally get this one in oxide forms. So this is one of the oxide form, which is therefore it can be bauxite or kaolinite. So these are different bauxite forms. So when it comes to the form, bauxite is generally available in different ores. So bauxite ores are available in India, mainly in Andhra Pradesh. We have different types of bauxite ores from where we get this aluminum. So we extract this one from the ore, bauxite ore, and then you transfer it through different process. We transfer it and you get as aluminum. So these are the different types of elements, whatever you can see in oxide forms. We have bauxite, we have bauxite, we have kaolinite, we have nepheline, and we have alunite. So it's generally found in mainly it's found in United States, Italy, and France. And the diagram below shows you about three different elements: bauxite pebbles, and we have different types of kaolinite, and also we have bauxite in the form of penny, also small bauxites. So it is not found in, but it's not been found in Thailand. But in Malaysia and Vietnam, you get this aluminum alloy. Thailand, you get other non-ferrous alloys, but you don't get aluminum from that, which Thailand gets exporting it from other countries. So this is about aluminum alloy. And when it comes to the attractive properties of this aluminum, so what does this? So when it comes to the attractive properties of this aluminum, it has high corrosion resistance. It has excellent machining properties, so you can machine it to the given substance, and also it's light in weight, and also it has high tensile thermal strength and conductivity, and also it has high ductility, and it can easily be deformable into different shapes. So why we need they have got a good properties when compared to other alloys. And also when you compare aluminum and steel, as you can see, the red one in the graph shows you about the aluminum. So the strength is quite higher. In every property you can see aluminum is far better than steel, but steel is less in cost when compared to aluminum. That's why everyone try to use steel. And also aluminum is light in weight when compared to steel, but steel is quite higher in weight. So this graph shows you the comparison of aluminum and steel. And what are the different types of applications of aluminum? So where we use this aluminum? So aluminum is used in automotive applications, where we use it in the wheel casing, we use it in the body frames of our cars, and it is used in construction equipment, it is used in packing, packing and containers, and also it is used in aerospace applications. So these are the different types of applications of aluminum. So when it comes to the history of production of this aluminum, where was this first done? The production process, where it was first done? First it was done in 1959 in France, and then it was done. The second one is done in Australia in 1888, and then in Germany, and then in the United States in 1976. So this is the different process whatever I've done. So the normal process of extraction is generally we tell it as Bayer process, which is invented in Germany. We try to use until now. So the other processes are not that much significant as shown. So Bayer process is invented in Germany, and it was introduced by Hall process. We call it as Hall Herotil process, or we call it as Bayer process. It's generally converted into that process. So when it comes to the extraction of this aluminum can be extracted from bauxite, it can be extracted from kaolinite and nephelinite. So it can be extracted in different forms. And when it comes to bauxite, we know that bauxite is generally having 30 to 50% of the bauxite what you're getting from ore. It has 30 to 50% of aluminum, so you can call it as aluminum oxide. It has 3 to 3% of silica. It has 10 to 18% of titanium oxide, and other balanced water. So the composition of a bauxite, what does bauxite have, is this one. So this is the composition of bauxite. And when it comes to the point of kaolinite, kaolinite has 30 to 32% of aluminum, which is Al2 aluminum oxide, because aluminum, once it's extracted from the ore, it is in the form of oxide. So then you try to do the process of extraction and refining, heat treatment, and then you get it as pure form in aluminum. But once you get it from the core, it's in the form of aluminum oxide, alumina. So you call it as alumina. You don't call it as aluminum. So kaolinite also has alumina. So alumina has 30 to 35%, and it has a balanced form of silica, and also it has water. So, and the third one is nephelinite. Nephelinite is having 30% of aluminum. It has 40% of silica and 20% of sodium oxide and potassium. Sodium oxide and potassium. So this is about the different configurations of the ores, whatever are available from the earth crust. And note that we have a note. The main thing is that extraction process of this aluminum requires high electrical consumption. So where we have electricity, so where is supplied more, they are going to have the extraction of this aluminum. So that's why we have a lot of this extraction process wherever the current is produced quite higher when compared to other states. In India, we have it in Andhra because we have a good production of this aluminum, and the production process is quite different, and also the extraction is completely different to other type of process. So the only process what I would explain to you is about Bayer process, which was invented in Germany and then consumed by US. So the Bayer process, what happens is the aluminum, whatever is extracted from the from whatever the materials I've told you, it's extracted from bayonet, bauxite, kaolinite, and nepheline, is generally extracted. So once this aluminum Al to aluminum oxide, whatever is extracted in the form of aluminum, is then digested through a crusher. So you send this bauxite into a crusher, and then this gets mixed with a strong sodium hydroxide, and this hydroxide solution at a temperature of 240 degrees centigrade. So whatever you get, the first stage where you're getting bauxite, this from the bauxite you're getting alumina is heated, or it is getting digested with bauxite. So alumina is getting digested from bauxite, and this bauxite is generally crushed. It's in form of big stones, and this is crushed with strong hydroxide, so NaOH. So bauxite and this sodium hydroxide, they get crushed together. The solution gets crushed together at a temperature of 240 degrees centigrade, and then after this step, it goes. The alumina is dissolved with sodium aluminate. Second process is whatever you're going to get. So in the first process, this one is getting aluminum oxide, what you're extracting from the bauxite in the presence of sodium hydride, sodium hydroxide, NaOH. So this is the first step what's happening. So whatever the thing, what alumina we're getting from the bauxite is mixed along with sodium hydroxide and heated at a temperature of 240 degrees centigrade. So once you heat at 240 degrees centigrade, then what happens is, whatever the extract you're going to get, the alumina, whatever you're going to get, Al2O3, whatever you get, is then dissolved with sodium aluminate. So you have dissolved this one with sodium aluminate. So once this gets dissolved with the sodium aluminate, we have a soluble solution water. So the first stage, whatever you see, the alumina is in solid state, but it gets dissolved with this sodium aluminate, it becomes a liquid state. So after this insoluble resides of this are in the form of red ingots. We call it as red ingots. Whatever you're going to get from this are called as red ingots, and these red ingots are composed with oxides of ferrous and also silicon. So this red ingots, what you're going to get after the mixing of alumina with sodium aluminate, you're going to get two forms. You're going to get alumina along with the forms of sodium and also silicon, which is removed. As you can see the equation below, as they showed you. So aluminum oxide, when it is reacted with water, it's going to, and also with the presence of sodium oxide, you're going to get sodium aluminate, and you're going to get hydrogen of water. So this is the general reaction what's happening here. So what aluminum in this Kroll process or Bayer process, in this Bayer process, and where the extraction of this aluminum, when the aluminum oxide, or which is extracted from the bauxite, is mixed with water and also in the presence of sodium oxide. So when it's mixed with sodium oxide, you're going to get sodium aluminate and water. So this is the general equation how you're going to get. So from this sodium aluminate, this is the second step. So whatever is happening, and when it comes to the third stage, second step, the second step occurs the decomposition of this sodium aluminate. So the decomposition of this sodium aluminate, so according to the stages what I've explained here, we have the first process where we have aluminum oxide. When it is reacted in the presence of sodium oxide in the presence of water, you're going to get two molecules of sodium. So I explained you as in the first step what you're going to do. So what happens in the reaction here is, so this aluminum what is extracted from the bauxite is mixed along with sodium hydroxide and water. In the presence of this, what you get is you're going to get sodium aluminate and water left over. So this is the first step what is happening in the Bayer process. When it comes to the second step, what you're going to do is the decomposed sodium aluminate, what you're going to get is mixed, it gives aluminum oxide, alumina, and also at a temperature of 50 degrees centigrade. So this is a reverse reaction which is achieved where the process of producing this aluminate is reacted with water. So you're going to get aluminum oxide and oxygen and water acts as a agent. So this is the compound whatever it's going to form. So in the final process, this water is removed. So from this Al2O3, the water is removed, and from once the water is removed at a temperature of 400 to 800 degrees centigrade, you're going to get the aluminum in pure form. This is the final step. So this diagram whatever is shown here shows you about the Bayer process, where you can see You can see the Bayer process I've explained you. We have bauxite which is crushed in the, you can see it's in the form of small rocks, and from here it is sent to the crusher and it is getting crushed and it is mixed with sodium hydroxide, where you can see the solution. From there you have in the form of red mud, as I told you, we have it in the red mud. The deposits whatever are found applied down, they go into the down position and they get crystallized, and the similar process occurs in everything. So this is about Bayer